Hello everyone, welcome back to another video discussion in strength of materials, and in this video we will talk about shear and moment diagram using area method. So in this video it is another approach in formulating a shear and moment diagram, and we will not be using shear and moment equation. So we will discuss on the easiest way in creating or formulating a shear and moment diagram. Okay, so we just need to do or to follow the procedure for area method, but we need to familiarize ourselves with these 6 rules in constructing shear force and bending moment diagram. So we have rule number 1: if we have P, or our concentrated load, that is acting downward, our shear diagram should also jump downward. Now, if we have our P, or concentrated load, that is acting upward, then our V diagram jumps upward as well, since we know that our P here causes discontinuity in our beam. Now, if we have rule number 2 here, if we want to compute the change in the internal shear between, like for example, x1 to x2, we just need to compute the area of our load diagram between x1 and x2 as well. Okay? Now, if we have at any location x, the slope of our shear diagram is equal to the intensity of the distributed load. Okay, so I will discuss it to you in my next slides. Now, for rule number 4, if we want to compute the change in the internal bending moment, what we're going to do is just compute the area of the shear diagram between that specific interval. Okay, like for example, if we want to compute the change in moment between x1 and x2, then we compute the area of our shear force diagram between x1 and x2 as well. Okay, then the intensity of slope of our moment diagram depends on the intensity of the internal shear force. Now, for rule number 6, if we have an external moment, and then we have an external moment that is rotating counterclockwise, okay, this one is negative moment. Okay, our moment diagram goes downward if we have a counterclockwise external moment or couple. If we have a clockwise couple or external moment, then our moment diagram jumps upward, since this one is positive. Now we have the relationship between shear and moment if we have positive shear. So I have discussed it already in my previous videos. So if you have our shear diagram that is in 0 order, okay, that is constant, therefore our moment diagram here should be in linear, okay, that is upward with a constant slope. Okay, now for a linear or shear diagram that is in the first order, our moment diagram here is the second order. But if our shear diagram is increasing, our moment diagram should be in smiling curvature. Now, for our shear diagram that is decreasing like this one, and it is in the first order, our moment diagram is in frowning curvature, and it is in the second order. Okay, so if our load diagram is in triangular, that is in the first order, then our shear diagram should be in the second order, and our moment diagram should be in the third order. For negative shear, if we have again this 0 order, we have our first order moment diagram, and it is in downward direction. Okay, if we have this shear diagram in negative shear that is decreasing, as what you can see here, and that is in first order, our moment diagram is in frowning curvature, and we have a quadratic or a second order moment diagram. Now, for shear diagram that is increasing like this one, we have our moment diagram that is in smiling curvature, and it is second order. So these are the relationship of our shear and moment for both positive and negative shear. Now let's try to apply these rules in solving problems. So I have here an example. We have to draw the shear and moment diagram of this load or this beam. This is a cantilever beam, since we have a fixed end here, and then we also have a concentrated load and an external moment in our beam. Okay, So the first thing we do here is to compute the reactions. Now, we know that we only have one support, so in our fixed end, we have three reactions. We have vertical reactions, okay, we also have horizontal reactions, and we also have moment. Okay, let's assume that the directions, okay, so these are all assumed directions, so therefore if we come up with a negative value in our answer, therefore we have incorrect assumption. So we know that at C we have the vertical reactions, the horizontal reactions, and the moment reaction. However, we know that we do not have a horizontal force along the beam, so therefore we could say that we do not have a horizontal reaction, and this gives us 0. So we have here, let's say this is our RC and this one is our moment C. So we need to compute the reactions. First, we can sum up forces vertical. It's equal to 0. Upward forces are positive. Then we have RC that is acting upward minus 20 is equal to 0. So we have our RC is equal to 20, that is in kilonewton. So we have RC here, that is 20 kilonewton. Now for moment reactions, we sum up moment at C that is equal to 0. Let's assume that a counterclockwise moment is positive. Then we have, that is, we have negative MC, since we know that this is in clockwise direction. Then we have plus 20, the concentrated load, times the moment arm from C. We have 6 meters, correct? You have 4 plus 2. Then we have the couple, or the external moment, that is 80 kilonewton meter, that is rotating clockwise. So we have negative 80. Okay? And is equal to 0. So we have our moment at C that is equal to 40 kilonewton meter. Okay? And we know that since we have positive value of our moment, if we simplify this equation, so therefore the rotation of MC, which is clockwise, is correct. So therefore MC is rotating clockwise. Okay, so we have all the reactions, so we can now draw the shear and moment diagram. Okay, let's now draw the shear and moment diagram. So we have already computed the reactions. That is, we have the reaction at C that is vertical, that is 20 kilonewton upward, and a 40 kilonewton meter moment reaction that is rotating clockwise. Okay, now in creating a shear diagram, we need to start, or most preferably, we need to start at the leftmost point in our beam. Now, the leftmost point here is point A. So we start at point A. We start at 0. This is the reference line. Okay. Now, at point A, we have a 20 kilonewton P load that is acting downward. And from our rule that if we have P load that is acting downward, then our shear diagram jumps downward. Okay. So therefore, from 0, we jump here. That is negative 20. Okay, that is negative 20. So we have at point A, we have our, let's say, our first shear that is negative 20 kilonewton. Okay, now after that one, we know that in between A to C, we do not have a uniform load nor a concentrated load. We only have external moment, but it won't affect our internal shear. Okay, since in internal shear, in computing the internal shear, we are just summing forces vertically, so we do not include moment. So therefore, since we do not have a load from A to C, so therefore we know that our shear diagram here is in 0 order. Okay, and that is in horizontal line diagram. So therefore we have our shear diagram here, that is this one. So at point C, we have negative 20 as well. Okay, so that's it's our V2, we have negative 20. Now, why is it negative 20? Okay, now take note, if you cut our section at this point here, or at any point between A to C, we could have exposed our internal shear that is in upward direction, since that is in equilibrium with 20 kilonewton. If we sum up force vertical, our shear here that is upward. Okay, let's say that's our V1. Now take note, since we have our shear is acting upward at the right face of our beam, so if this is our beam, and then we have our V here that is acting upward at the right face, so therefore that is negative. Okay, but if we have internal shear that is acting downward at the right face, then that is positive. So that's why we have negative internal shear from A to C. Now at point C here, we have a reaction that is acting vertically, that is we have 20 kilonewton. So therefore at point C, we have let's say our V3 here that is equal to negative 20. Let's start at negative 20. Then we have a reaction that is plus 20, that's positive. So therefore that is equal to 0. So therefore we end at 0 at point C. Okay, so our shear diagram here ends at 0. So that's how you are going to check your shear and moment diagram. Okay, if your shear and moment diagram closes, that means you have draw the shear and moment correctly. Otherwise, you have to review your solutions. You might be wrong in the computation of reactions and so on. Okay, so that always ends at 0. So we have now our shear diagram. Now let's try to create a moment diagram. Now let's start at the leftmost point. We have point A, and we know at point A we do not have moment since this one is free end. Okay, so therefore we start at 0. So we have here moment 1 at point A that is equal to 0. Take note, at point B, we have our moment that is clockwise, so therefore we need to include that in our moment diagram. So we compute, or we determine first the location of our moment at point B. So we have from this point to point B, so from point A to point B, our change in moment is equal to the area in our shear diagram. So therefore the change in our moment is equal to the area of our shear diagram, that is from a specific interval, let's say from A to B. So we have here at moment B, let's say that's a moment at B, at point B, let's say that's moment 2, that is equal to our moment 1 plus the area of our shear diagram. Okay, so we have our moment 2 here that is equal to, our moment 1 is 0, correct, plus the area of our shear diagram. Now from A to B, we have the area that is in rectangle. Take note, we only computing the area at this point. Okay, and that is, we have negative 20. Okay, since that is negative shear, then times the length, that is 4. Okay, so therefore our moment 2, or at point B, that is equal to negative 80 kilonewton meter. Okay, since negative 20 here is in kilonewton and 4 is in meters, so we have our moment that is negative 80 kilonewton meter. So we have here, from B, we have negative 80, so we go down at this point. So let's say we have negative 80 kilonewton meter. So since again, our shear diagram is in 0 degree, our moment diagram should be in the first degree. So therefore it is just an inclined line having a constant slope. And then we have this our moment diagram from A to B. Okay, now at point B, we have a couple or external moment that is rotating clockwise. Since we have clockwise, that means this is positive. So therefore, we have our moment 3 here, that is the moment 2 plus the moment or external couple. We have moment at 3 is equal to our moment 2, we have negative 80, plus our couple that is positive 80, correct, since that is clockwise. So we have our moment 3 here that is equal to 0. So therefore, we have our point at 0. So jumps at 0 moment. Okay, that's the location of our new moment. Now from B to A, we have the area of this shear diagram. So this one. So therefore, let's say it's our moment 4 that is equal to moment 3 plus the area of our shear diagram. So we have moment 4 is equal to our moment 3 is 0, correct? Then plus the area of our shear diagram, that is negative 20, this one, times the length, that is 2 meters. So we have times 2. So therefore, our moment 4 is equal to negative 40 kilonewton meter. Okay, so therefore, we plot at this point, that is negative 40. Okay, so at point C, we have here negative 40, and that is we have, since this is in 0 degree, so therefore we have first degree moment diagram, and this is negative 40 kilonewton meter. Now to check if our moment diagram closes, so we have our, take note, we have our moment here, it is 40 kilonewton meter reaction, and then it is acting clockwise, as what you can see here. That means it is positive. So therefore, let's compute our moment 5. So we have our moment 5 is equal to moment 4 plus the moment reaction is equal to our moment 5 here is equal to moment 4, that is negative 40, correct, the initial moment, plus the moment reaction, that is positive since it is clockwise direction. So we have 40. So therefore, our moment 5 is equal to 0. So our moment diagram is correct since we ends at 0. Okay? So this is our moment diagram. So imagine how easy this method is compared to the conventional approach, that is using shear and moment equation. And then we have our second example here. We have to draw the shear and moment diagram using area method and determine the moment at 4 meters from A. So again, the first thing we do here is to compute for the reactions. So we have 2 reactions here. We have the reactions at B and D, but in B here we have vertical reactions. It is hinged, so therefore we should have a horizontal reaction, but take note, in our beam we do not have horizontal forces, so let that be equal to 0. Now for D, that's ruler, so we have vertical reaction, let that be as RD. So we compute for the reaction B and D by, let's say, summation of moment at D is equal to 0, and we have the force or the moment that is counterclockwise, it's positive. So we have here, that's RB, that's negative since it is clockwise, times the moment arm, we have 1.2 plus 3.3, that is 4.5, that's the distance from D. Then we have plus 3.2, the concentrated load at A, times the moment arm from D, that is 6, okay, plus the concentrated load 7.2, that is the times the moment arm, that is 3.3. Then we have the distributed load. Now our uniform load here from A to D is 3 kilonewton per meter, correct? So we need to compute its resultant, that is 3 kilonewton per meter times the entire length. What is the entire length? That is 6 meters. So we have our resultant for 3 kilonewton per meter, that is 3 times 6. Okay, so that is 18. And the location of our resultant force is 3 meters from D, since 1/2 of its length of action, that is 6 meters. So we have 6 divided by 2, that is 3 meters. So we have 3 meters from D. Then the rotation is positive, no, since that is counterclockwise, plus 18 times the moment arm 3 is equal to 0. So we have our RB here, that's the reaction at B, is equal to 21.547, that is in kilonewton. Okay, now let's compute the reaction at D. So we have to sum up forces vertically, that is equal to 0. Upward forces are positive. Then we have RB plus RD minus the concentrated load 3.2 minus 7.2 minus 3 times 6. That is the resultant of our uniformly distributed load, and this equals to 0. And we know that RB here is 21.547, so plus RD, let's copy everything here. 6 times 2, that's 18, is equal to 0. So we have our RD that is equal to 6.853 kilonewton. So that's the reaction at D. Okay, since we have already computed all the reactions, then we can now proceed to the shear and moment diagram. Okay, so let's start creating our shear and moment diagram. So let's start at the leftmost point of our beam, that is at point A. So we start at A. Okay, so we have, let's say that's our V1. So our V1 here, that is 3.2 kilonewton. Since we know that we have, that's negative 3.2 kilonewton, since we know that we have P load that is acting downward. So therefore, from 0, we go downward, that is negative 3.2. Let's say at this point, negative 3.2. Now, in between A to B, now if you want to plot our shear here at point B, we need to compute the area of our load diagram at point or within A to B. Okay, so we have, let's say that is the shear 2, that is equal to shear 1 plus the area of the load diagram. Okay, and this gives us our shear here, that is equal to, the first shear is negative 3.2 plus the area of the load diagram, that is 3 kilonewton. We know that this uniform load here is 3 kilonewton, and then we have the length of 1.5, and we know that it is downward, so therefore that is negative. So we have times negative 3 kilonewton per meter times the length, that is 1.5. This is a rectangular area, so it is equal to negative 7.7 kilonewton. So at point B we have negative 7.7, so we go at this point, let's say at that point, negative 7.7. So again, since we have a 0 degree in our load diagram, so therefore we have first degree in our shear diagram. Okay, now at point B we have an upward reaction, that is 21.547. So therefore we have our shear 3 here, that is equal to negative 7.7, that is upward, that's positive 21.547. This equals to 13.847 kilonewton. So that's positive. So therefore we go above our reference line, that is in 13, let's say at this point. So therefore we jump from negative 7.7 to 13.847. And now we can now determine our shear point at point C by computing the area between B to C, and that is the area of our load diagram. So this one, this area, and we have here, let's say that's our V4, and this is equal to the initial shear, it is 13.847. Then we have plus, then take note that our load here is acting downward, so therefore that's negative 3 times the length, that is 1.2. That's the area of the rectangle. And this equals to 10.247 kilonewton. So we have here 10.247 kilonewton. So at this point, let's say at that point, since this is in 0 degree, so we have our shear diagram that is in the first degree. Now at point C, we have a P load that is acting downward. So therefore, we have our shear 5 that is equal to the initial, that is 10.247. Then we have negative 7.2, okay? This negative 7.2, and this gives us 3.047. So we have here let's see at this point, 3.047. Okay, now we can now plot our point at point D by computing this area from C to D. Then we have, let's say that's our V6, that is the initial, that is positive 3.047, plus the area, that is negative 3 since it is acting downward, times the length, that is 3.3. This equals to 6.853, that is in kilonewton. And therefore, in our point D, we have negative 6.853 kilonewton. So at point D, we have negative 6.853. So at this point, let's say, so disclaimer, I have not drawn this shear diagram in scale due to limited space. Okay. Now, after point D, take note we have a reaction that is acting upward at D. So we have our shear force 7 that is negative 6.853. Since our reaction here is acting upward, so we have plus 6.853, and this gives us equal to 0. So we have closed our shear diagram, so therefore we have correct diagram. So I made a slight revision in our shear diagram so that it would be drawn in scale. So I have this final shear diagram, and it ends at 0. So we have correct shear diagram. So our moment diagram here will be based on the area of our shear diagram. Okay, so let's try to start at the leftmost point, and that we start at A. So we have, let's say that's our moment 1 at A. So since we have free end at this point at A, so we have 0 moment. Okay, so we start at 0, okay, at point A. And then we can now plot our moment at point B at this point by computing the area between A and B. And this area here is in trapezoid, correct? And the area of a trapezoid is in terms of 1/2 height times base sub 1 plus base sub 2. And this is what this base here are parallel. So therefore, our moment 2, that is equal to our moment 1 plus the area of our shear diagram, and then we have our moment 1 that is equal to 0, that's our first moment, then plus, now take note we have negative shear here, so that is a negative, so we have times negative 1/2, then the height is this length here, this is 1.5, okay, 1.5, and the parallel base, that is 3.2 plus 7.7, okay? So we have 3.2, this the height of this point, and the height of this base is 7.7. So we have 3.2 plus 7.7, and therefore we have moment 2 that is equal to negative 8.175, that is in kilonewton meter. So it is negative, so therefore we go below the reference point or reference line, that is we have negative 8.175 at this point. Let's say at this point here, that is negative 8.175. Okay, now what is the curvature? Since we know that this is in the first degree, our shear diagram, so therefore our moment diagram should be in the second degree order, so it is a curve. But the curvature is, since we have a decreasing shear diagram here, so therefore we should have a frowning moment diagram. So we have our moment diagram like this one that is frowning. And then let's locate the moment at C at this point. So by computing this area first, so therefore our moment 3 that is at point C is equal to moment 2 plus the area of our shear diagram, and this equals to, our moment 2 is negative 8.175, and since we have positive shear, so we add, then this is trapezoid, that is 1/2 times the length, that is 1.2, okay, times the height, that is 13.847, plus the height of the other end, that is 10.247. So therefore, we have our moment 3 that is equal to 6.2814, that is kilonewton meter. Okay, so we move upward, that is from 6.2814. So let's say at this point here. Now, the curvature is in second order, and since our shear here is decreasing, so therefore we have frowning moment curvature. Okay, so we have, okay. Now take note, we still have positive shear. At this point is positive shear. So therefore, we need to calculate this area. So how are we going to calculate this area? So take note, we should have the length here. Let's say that's x. Okay, so how are we going to compute for x? Now we know that if we have x here and the entire length is 3.3 meters, this one, the entire length from C to D, so we could have this length, that is what? 3.3 minus x, correct? So therefore, we can use ratio and proportion. Okay, that is length is to length and width is to width. So we have our ratio and proportion, that is 3.047, that is this height, over the length, that is x, is equal to the height of the bigger triangle, that is 6.853, and the length of the bigger triangle, that is 3.3 minus x. So we could compute our x here, that is equal to 1.016, that is in meters. So therefore, at this point, diba, at this point, that is where our internal shear is 0, okay, at that point. So if you want to use the shear equation, then you let V there as equal to 0. But if you are using area method, then you can use ratio and proportion, since these are triangle. So we have here that is 1.016. That is the length from C to this point. Okay? Now we can now compute the area of our small triangle. And then we can now compute the moment at this point. So we can now compute the moment at this point. So we have, let's say that's our moment 4. So our initial moment, that is 6.2814. And since our small triangle there is a positive shear, so we have plus 1/2 times 3.047 times the length, that is 1.016. This is an area of a triangle. And this gives us the value of our moment at 0 shear equals to 7.829. Okay, that is in kilonewton meter. So therefore, we have here at this point, okay, that is 7.829. So since again this is decreasing shear, so we have a frowning moment curvature. And then we can now compute the moment at point D by computing this area. And this gives us the moment 5 is equal to the moment 4, 7.829. Okay, since this one is negative shear, so we have minus 1/2, that's the area of a triangle, times 6.853 times, now take note, our length here, that is 3.3 minus x, so therefore this is 3.3 minus x here is 1.016. We have computed the value of x, this one. So we have the answer is equal to 2.284 meters. So therefore, we have 2.284 distance from this point to point D. So we have here 2.284. And we have our moment 5, that is equal to 0. So therefore, we end at point 0. So this means that we have closed our moment diagram, thus we have drawn the shear and moment correctly. So this one now is our shear diagram, and this one is the moment diagram. So this is how you are going to compute or to draw the shear and moment diagram using area method. And then we still have another question, and we need to determine the moment 4 meter from A. So we have 4 meter from A, so this one, let's say at this point, okay, this is 4 meter from A. So we can use cut section, we can use shear equation, or we could also use by inspecting the shear and moment diagram. Now, since we are asked to compute for the moment at 4 meters, so let's say at this point, okay, that is 2 meters from D and 4 meters from A, okay, since we have 6 meter length. So how are we going to compute for our moment? So you can just again, you can either use shear equation, moment equation, or you can just cut at this point, then sum up moment, or you can just use the shear and moment diagram. Okay, so we know this is 2 meters. So we need to identify the moment at this point. Okay, so at this point here. So to compute for that moment, we need to identify first the area of this point, okay, of this shear diagram, this area, this small triangle here. So we can do ratio and proportion. Okay, so we know that this length here is equal to 3.3 minus 2, and that gives us 1.3. So we have 1.3 here. Okay, so this one is 1.3. If we isolate this portion of our beam, this one, okay, from C to C prime, which is again 4 meters from A. Okay, so therefore, if this 1.3 and 1.016 from C to 0 shear, so we have value of x, that is 1.3 minus 1.016, that is 0.284. We know that from C to 0 shear, it is 1.016, so we solved this a while ago, correct? So by ratio and proportion. So we have 0.284, that is the length from 0 shear to C prime. So therefore, the length from this point to... So we can now compute the moment at this point here by using the equation. Let's say that's our moment at 6 meters is equal to, that is the initial moment, that is 7.829, correct? This moment at this point, that is 7.829, minus this area here, okay? And this area is in triangle, that means we have 1/2 times 0.284 times this height. We do not have this height yet, so we can use ratio and proportion. That is, we have, let's say this is y. Y is to 0.284 is equal to, that's the height of this triangle, that is 3.047 over 1.016. And the height of our small triangle is equal to 0.852. So therefore, we have 0.852 as our y. So we multiply it here, that is 0.852. This is the area. Again, this is the area of this region here. Okay, this triangle. So you have our moment at 6 meters from A, that is equal to 7.706, that is in kilonewton meter. So therefore, the moment at this point is equal to 0.706, that is in kilonewton meter. So this is the moment 6 meters from A. Or we can use another approach by cutting at this section here. So we can cut, let's say this is our beam. So if we cut, we have 2 meters from D, correct? And then it would have our internal shear and internal moment exposed. So we have, let's say, this our internal moment, and this is 3 kilonewton meter. We also have reaction at D that is equal to 6.853. That is, you can now compute, or you can now sum up moment from, let's say, this is our C prime. Okay, that's C prime is equal to 0. Then counterclockwise positive. Then we have 6.853. That's positive times 2 since it rotates counterclockwise. Minus 3 kilonewton per meter, the resultant, times 2, times the moment arm, that's the 1/2. That is 1/2 of 2, that is 1. So you multiply 1. Then we have the internal moment here that is clockwise, so therefore we minus M is equal to 0. So we have M here that is equal to, that is positive 7.706 kilonewton meter. So this is positive, okay, and this backed up by our moment diagram here, in which our 7.706 is also in positive. And that ends our problem number 2. So let's solve another problem. We have